A question we often like answered is to determine how large our sample should be so that we can control the width of the confidence interval, so that we can say that our true estimate is likely to be within a certain distance. Now, there's a technical term for that. We call that the error, right? The error you commit by estimating mu via the sample mean is going to be, in general, smaller than the radius of the confidence interval. And so if this is a 100 times 1 minus alpha % confidence interval, say a 95% confidence interval or 99% confidence interval, you can actually compute the radius, right? It's going to be the alpha divided by 2 percentile, so 2.5% or 0.5%, depending on if you want a 95% or a 99% confidence interval, times the standard deviation, assuming you do know it, divided by the square root of the sample size. And so if you want to control the error, if you want to make sure that this radius is below a certain point, right? If you say I'd like this thing here to be smaller than E or larger than E, well, usually you'd want it to be smaller than some error. The only thing you can really do here is to control the sample size. Sigma you have no control over. That is part of the distribution of underlying values. Said alpha 2, I mean, you can control the alpha, right? A 95% confidence interval will tend to be shorter than a 99% confidence interval, but that's not really controlling. You can't really change that just to get tighter results. Because if you do change the alpha to get a tighter radius, well, you're also reducing the confidence that you have, that mu is actually going to be in there. So the one you can switch, the one you can control is the sample size. So if the error is meant to be larger than this thing here, in other words, if the radius is meant to be smaller than some error, well, you rearrange the terms, multiply by square root of n on both sides, divide by e on both sides, and then square both sides to remove the square root, and you end up with a sample size which is bounded below by this expression. And that's going to guarantee that your error is smaller than E. Let's look at a few examples. First, we'll select n observations from some normal population. We don't know the mean. I mean, that is what we're trying to determine, but we do know that the standard deviation is sigma 100. What sample size should you use if you want to make sure that the error on the population mean estimate is at most 10 units at a confidence level alpha 5%. So what you're saying here is that you will compute the sample mean, and then you'll build a 95% confidence interval. And what we know is we know the length of this radius here. This is going to be the 2.5th percentile of the standard normal distribution, because if alpha 0.05, alpha divided by 2 is 0.025, times sigma, which we know to be 100 in this specific example, times the square root of n. And we would like this quantity here to be smaller than E, which in this case is 10. So we just flat out use the formula. We solve for n. It gives us the 2.5th percentiles times 100 divided by the error 10, square all of this, you get 19.6 squared, which is 384.16. So as long as you pick a sample size which is larger than 384.16, so 385 and up, then you know that the error you commit by using the sample mean to estimate mu will be at most 10 with 95% probability, and with the caveat here that our interpretation of what it means to have 95% probability is how we've described confidence intervals in the previous sections. We're not really saying that we're 95% sure the true mean will be within 10 units if we pick an n value of 385 and up for this normal population with standard deviation 100. What we're saying is that if we were to repeat this process over and over again, in about 95% of the cases, would we find the true mean within the confidence interval that we have built. Now, if the standard deviation in the population was different, here let's say that it's a tenth as large as it was previously, how many observations do we need in our sample to guarantee that we'll be within a certain error bound? Well, you put it in there and you'll see that you get a substantially smaller number here, 3.84. So as long as you had 4 observations or more in your sample, you know that you would be within 10 units of the true mean if you estimate it with the sample mean. And that number is substantially smaller because if the underlying distribution doesn't have as much of a spread, if the standard deviation is smaller, so this was the original one, this is this other one that we have here. If the distribution doesn't have as much of a spread, there's not as many chances that you will pick values that are very far outside the reasonable range. And so when you compute the average, because a lot of these values will be closer together, the average is going to be closer together. And that's going to reduce the size of your confidence interval to start with. Given that the error hasn't changed, it's still 10 in both cases. And what this means is that you need substantially fewer observations to be able to guarantee that your mean is well approximated by the sample. On the other hand, if the error bound shrinks, well, the fact that this is part of the denominator means that you would expect to need more observations to be able to ensure that your sample mean approximates the true population mean within the error bound. If we reverted to a standard deviation of 100 here, but this time we wanted an error bound of 1. So we wanted to make sure that if this was our 95% confidence interval, that this distance would be at most equal to 1. We would need to have at least 38,416 observations. Right? The error bound is very, very, very small. So for this confidence interval to be small, we need a very large sample size. And if you change the confidence level, if we go from 95% to 99%, in this case, the alpha is the thing that changes, and so you're using a different bound here. So now we're reverting to our original standard deviation and original error bound. You compute the quantity, right? The 0.5th percentile is 2.575. Multiply by 100, divide by 10. That's the same thing as multiply by 10. Square that, 663. So as long as you had 664 observations in your sample or more, then you would be 99% certain with the explanation we've given of what that means before, that the sample mean would be within 10 units of the true population. So the relationship between alpha, sigma, the error bound E, and the sample size isn't always intuitive. I mean, it's a fairly straightforward expression here, but the percentile computation sort of complicates matters in terms of our ability to quickly guess what the value should be. Like once you know deep in your soul that the percentile for the 95% confidence interval is 1.96, and once you know that for the 99% confidence interval is 2.575, then perhaps you can start intuitively guessing what these numbers would be. But until you've really absorbed that, it's always a bit of a surprise what the sample size has to be in order to meet the requirements of the